We are doing rectangle trapezoidal approximation today, but let's compare our answers with the left rectangle and right rectangle we did before. What was the answer to left rectangle? I think it was 14, was it? And the right rectangle, this thing does not want to write. Right rectangle was 30, and mid rectangle, the most accurate one, was 21. Okay. Now, today is a trapezoidal approximation. What that looks like is this. Instead of drawing left rectangle, like let's just take this one. What is wrong with it? Left rectangle like this, or instead of drawing right rectangle like this, we draw a trapezoid. Okay, so it's going to look like this. Let's take that again. Draw trapezoid. That looks like that. You get it? And each of them, first one is not exactly a trapezoid, it's triangle, but because this endpoint is 0, but you see a bunch of trapezoid. And you can technically say that's a trapezoid with one base being 0. So we have 4 trapezoid. You get the idea? So let's do it. Do you remember the area of the trapezoid formula? Uh-oh. Was it base 1 plus base 2, and then multiply by the height and divide by 2? Okay, let's erase this evidence because it's embarrassing. This is calculus BC, you should know this. Oh no, we have this in recording, so this embarrassment will live forever. Okay, trapezoid. Okay, let's say this is for other students out there in the world, not Peninsula High students, because none of you needed this, right? It's for the public service in case students out there, PB High and all, who forgot area of a trapezoid formula. So the width in this case is always 1, isn't it? Which is the, look at it sideways, that's the height of the trapezoid, and this is base 1 and base 2. You get it? So trapezoid, first one is really a triangle, so 1/2, right? And then times base, which is 1 times the height. Oh, let's write the data points. This is 0, this is 1, so 1 square, and this is 2, so we have 2 square. We have 3 here, so 3 square, and 4 here, and so 4 squared, eh? So we have 1 times 1 square plus, and then also 1/2, right? That's 1/2. We are thinking of it as height divided by 2 in that trapezoid formula I just erased, right? You have to divide that by 2. That's a part of the trapezoid area formula. And then we have 1 square plus 2 squared, eh? Right? These two. Let me change the first ones to be consistent. I'm gonna say this is a 0 square. Why doesn't it want to write 0 square plus this writing device, you know? Okay, let's try that again. I'm gonna zoom in a little bit. So we have still does not want to write, right? 0 square plus 1 square. Okay, and then we have 1 square plus 2 square, these two, and the next trapezoid will have plus 1/2, and then 2 square plus 3 square. Are you getting this? 1/2 times base 1, base 2. Okay, and then final one is plus 1/2, and then 3 square plus 4 square. You get it? Okay, how many of you can add fast? Let's see who comes up with the answer first, without the calculator. 1/2 is a common factor, so you're doing 0 plus 1 plus 1 plus 4 plus 4 plus 9 plus 9 plus 16. Who's got the answer?
22?
Yes. Did you do it without the calculator? Or did you cheat? Of course you didn't cheat, right? Yeah, okay, sure. Okay. Now, let's compare this with left and right rectangle or mid rectangle. You know our true answer was, right? What was our true answer? Let's just write it up here. Our true answer, which I will call from 0 to 4 of x squared dx. You know what I'm saying? Integral answer. And that was 21 1/3, wasn't it? So it's not as accurate as mid-rectangle here. But it's pretty close. And this is so much easier to do than mid-rectangle, because remember how painful mid-rectangle was? Okay. Trapezoid is one of the more beloved approximation of integral in applied mathematics. Applied mathematicians and the programmers love this one. It's so easy to do. And actually there is some deeper thing. I mean, you can make it whole lot more accurate than it really is without using that much CPU time, computing power. This is one of the more efficient one out there. So this, they love it. This is a big deal, okay? Now, but you notice that in comparison to the left rectangle and right rectangle, do you see the relationship of this and between these two? What is the relationship? Oh boy. Do you see this trapezoid happens to be the average of the two? I mean, in this case it is, right? If you add the 2 and divide by 2, then you get 22, don't you? But is it always the case? Can you tell by looking at this and remembering back into left rectangle and right rectangle? Or can you think like this? It's called the median. What was the median of a trapezoid? I'm gonna put it right here. This is a median of a trapezoid, isn't it? How many of you remember this as a median? Median is the average of these two, correct? Actually, I'm gonna write this down. Now it's like more. Trapezoid is h divided by 2, and then what we have is a b1 plus b2, correct? Why did I write it so high? This is a trapezoid area, but let's think about it like this. H and then b1 plus b2 over 2, right? This is what they call the median, and that happens to be the length of this thing now, isn't it? So it is h times m. You get it? And there's a median. M, of course, is equal to b1 plus b2 divided by 2. Do you believe it? And then when we do left and right rectangle, we use this. So of course it has to be the average of the two now, wouldn't it? If you just look at each trapezoid as the average of two rectangles. You know what I'm saying? Okay, so that's why your rectangle approximation program does not have a trapezoid in it, because you have the left and the right and you have a calculator in your hand. So you should be able to figure out the average of the two. You get it? Okay, and this time it was not as accurate as mid-rectangle, but because of the concavity of this thing, this is consistent over approximation. But if this concavity changes, then this trapezoid becomes really, really, really accurate. Well, precise. Precision is a better term than accuracy. Find the volume of this pond by using trapezoidal rule, okay? And the depth is constant at 20 feet. Oh, hold on, I screwed up assembling this writing device. Okay, so depth is 20 feet. So if we just look at this little section, let me just take this one as an example. We draw trapezoid like this. That didn't work now, did it? Okay, trapezoid like this, forget this drawing tool. And then we can think of that as 3D shape. Water. You know what I'm saying? So we can calculate the volume. Each of this is the dV. So this dV is still, so this is 20 feet here. And this, let's say, is B1, and this is B2. And the thickness, let's say, here to here, like that. And that happens to be, how much is it increasing by? 600? Is it uniform at least? How are they cutting this?
It's every 200 feet.
Every what?
200 feet.
2 feet?
200.
200, like that.
Yeah.
You know what I'm saying? So let's think about this. So this is, the volume of this is just the area of the trapezoid times 20, isn't it? So area of the trapezoid is 200, and then divide that by 2, height, divide by 2, and then B1 plus B2. And then we still have to multiply that by 20 feet. You know what I'm saying? Do you know what I'm saying? Okay, let's just simplify this thing. Do you see that 2000 times B1 plus B2? I'm simplifying this one formula because we have to do this a lot of times. You know what I'm saying? Are you with me? Okay, yeah. Now, then we'll compute the volume of this using trapezoid rule. Okay, so your volume is equal to 2000 times the first one, which is 0 plus 520, plus the second one, which is 520 plus 800, plus the third one, which is 800 plus 1000. You know what I'm saying? But then there are two of each because this has a uniform thickness. The reason that we can have a common factor like this is because this 200 is exactly uniform. You know what I'm saying? So I'm saying, why am I even doing this way? Then I can say, we'll say 2 times 520 plus 800 plus 2 times 1000, continuing down here, plus 2 times 1140 plus 2 times, somebody punch the calculator as I do this, 1160 plus 2 times 110 plus, continue down here, 2 times 860 plus 2 times, oh no, there's no 2 times now because that's the last one, and last one does not have 2. 860 is the last one that will have 2 and then plus 0. How about that? Good. And somebody punch the calculator and tell me what this is. I'm going to change this to approximately equal to while I am at it, because this still is a trapezoid approximation. Ethan.
26,360,000 cubic feet.
26 million, and then?
360,000.
Like that. Wow, that's a lot of water, but that's pond, okay? It's still a pond, so it's supposed to hold a lot of water. You know what I'm saying? You get it? Okay, this later becomes a big deal in chapter 7, so Yeah. Keep this concept relatively fresh. And then part B, you can just multiply this by fish density. You know what I'm saying? Which I don't want to do. Okay, then let's do this beautiful, beautiful electricity problem. Okay, when you say electricity, do you happen to know the voltage out of your wall outlet in the United States?
110.
110, 115. It's like roughly. This problem is saying 115, 110. I mean, officially they say 110, right? What does that mean? What does that mean? Okay. See, if you have your battery that you put it into your electronic devices or your phone, rechargeable battery, let's say 1.5 volt is a constant function. You know what I'm saying? It looks like this. Output is exactly like this. Actually, it's not even exactly like that. It's supposed to be like that, but as the battery discharges, it loses its voltage too. So it's like it goes down. But still, this part, it maintains its constant output. But do you know that this thingy is not really direct current? It's known as the alternating current, which looks like this. It's a sinusoidal function. Did you know this? Oh, okay. It actually, you ever wonder there's no plus and there's a minus on these outlets? One is usually bigger than the other, so you cannot flip it over, but some devices actually, they have exact same thingy plug. So if you flip it over and plug it the other way, it still works. Do you ever wonder how does that work? Because in regular battery, if you put it in the other side, it doesn't work, right? Because there's a direction. There's no direction because it actually direction changes. Well, how frequent does it change, which is called the frequency? What's the frequency of your outlet? They say 60 hertz, meaning 60 times 60 cycles in 1 second. Whoa, so this is really this kind of function. But, let's go back. What am I doing? Let's go back, undo. What do we mean by this 115 or 110 volt then? Does that mean our amplitude here is 115? No, because do you remember average value of the function? Average is not, I mean, this is like at the peak, so that is not powerful enough. So we need to know how high that maximum amplitude is. You know what I'm saying? Okay, and then what is the name of the physicist that came up with this alternating current? Very eccentric physicist, and if I tell you, you would know the name. Very famous physicist, because Edison is the guy who came up with the direct current, and then he created a company and is doing that. And this physicist said, well, my alternating current is better, so much better, like more efficient. We can transmit it over the long lines, and it became kind of rival of Edison. What's his name?
Tesla or?
Tesla is his name. Oh, so you know where Elon Musk got his name of his car, right? Tesla. Tesla is the guy who invented alternating current. Okay, so how are we supposed to do it? Okay, we'll start. So whatever it is, this function v as function of t is supposed to be some amplitude, which is what they are calling b max here, our a, and then sine, and then this used to be b in your pre-calc, but then physicists use omega t. And this happens to be if you have a unit circle thingy rotating, and that therefore creating sinusoidal function. It happens to be exactly that angular velocity. So for that reason, this omega, your b, is known as angular frequency. Okay? So far so good? Now, how can we figure out the relationship between these things now, right? Do we know the period? Okay, it's 1/60th of a second, but okay, suppose you don't know that. Do we at least know this is 60 Hertz? Yeah, it tells you 60 cycles each second, okay? So let's get this thing. Those of you taking physics, it comes in handy in EM. Review, pre-calc. Your period was 2 pi divided by B, right? Omega, B. So far so good? That tells you then your omega, which we need to figure out, which is 2 pi divided by period. You know what I'm saying? Say yes. Now, let's see if you agree with this. Frequency meaning there are 60 cycles in 1 second. Therefore, length of 1 second is 1/60. You get it? They are reciprocals. Good. Now, if you plug it in here, then omega now becomes 2 pi times frequency. This is kind of a handy thing to have, right? So do you multiply this 60 times 2 pi? So we have 120 pi. So far, so good. Okay, then let's graph one cycle, shall we? Say we have one cycle of pi, the sine graph right here, which will look like this. Okay, so this right there is one period cycle. So this is 1/60th. Okay, and this amplitude is what we are calling Vmax. And that cannot be 115. Because then average value of the function really is a lot lower. So when they say 115 volt, that means the average amount of voltage. So therefore you can calculate the average power. You get it? That's 115. So what is this then? Well, why don't we find the average value of the function? Do you remember average value? You know, average value of the function in case don't write this yet. We do it like this. Integral from 0 to 1, right? And then sine, we put Vmax, and then sine omega, which is 120 pi t. And then we divide that by 1. You know what I'm saying? Do you see this? What is the problem if we do this? Guess what we are going to get as an average value?
0.
We get 0. Why is that? Well, half of the time this is negative, and this area is exactly same as that area, so that gives you. Of course, that's useless average now, isn't it? Now, those of you who have taken stat, do you remember what standard deviation is? Error calculation. Do you remember you have to square everything, then add them up, and then take a square root and divide by it? Who comes up with that stuff? The reason for that is half of the error is more than your average, and the other half is less than your average. So if you add, they tend to cancel. The positive numbers and negative numbers tend to cancel and give you an illusion of your error is much smaller than what really is. You can't do that. So either you can take absolute value of everything and then add, or you can square everything and then add and take a square root. You get it? So that is known as the Euclidean norm, and that's like big I don't want to go into that detail. So typically what they do is, let's square it. If you square this function, then it's going to flip up and become a little bit sharper. And then we'll take an average. Then we'll take a square root. You get the idea? You get the idea now? Okay, so we're not going to do it this way. We're going to square it, but I need a little more space. So I'm going to push this thing down. So let's take a square of this. V square, our function square is V max square. I'm going to zoom in a little bit. And then we have sine. This thing does not want to write. Sine square, and then 120. I hate writing. I write it 120. I didn't write it in Dropbox note, but pi t. Good. Now, do you see the problem with this? We don't know how to integrate this now, do we? But I told you there's that identity that will be on at least 5 different tests. Yeah, let's use that. What was a sine square? Oh my God. Let's do it on a side. You remember forgetting this one? Yeah, okay, so we'll use that. So we'll put V max square over 2 out here, and then this will be 1 minus cosine, and we are supposed to multiply this by 2, right? Okay, so 240 pi t. Are we good? Are we good? Okay, now we are ready to integrate this. So this is average of V square now, and then this is V max square, and I'll just write it, and then I will write one more time. So this is V max out here, square out here, and divide that by 2, and 0 to 1 of 1 minus cosine 240 pi t dt. You with me? Say yes. Okay. So that becomes V max squared over 2, and this becomes t minus, this is how I do it, it's going to be sine, and then backward chain rule, right? If I differentiate this, this thing comes to the front, right? So I have to put 1 over 240 pi and 0 to 1. Good? Say yes. Okay, 1 here gives you 1. 1 here, that's still 0, isn't it? Sine 240 pi is 0. Everything else is 0, so what we get is V max squared over 2. You with me? Say yes.
Yes, yes.
Okay.
Yeah.
Then what do you have? Finally, now let's find out. So your average, this average is what they are calling VRMS. So here, I'm going to do it here. VRMS is really what they mean by average of the V. Square, okay? Now, so, and that to be our V max squared over 2. Good. Now we have to find VRMS. Oh, VRMS is the square root of this. Good. This is not square, so these are squares, so we have to take a square root. Okay, then that tells you our Vmax that we wanted to find out has to be square root 2 of VRMS. RMS meaning I'll just write it, 115 volts. Volt. How about that? So when we say somebody punch the calculator, what is 115 times square root 2? Oh, come on. Okay, whatever. That is the,
162 something.
So it's 162 volt-ish is what's coming out at the peak, the amplitude of that thing out of your wall. Okay. Okay. Any other question?
Yeah. Can you explain how you got to 1 minus cosine 240 pi t again?
Oh my God. Let's go back here. This, right?
Oh. Oh yeah.
Oh yeah. You want me to explain how I got that too? I can do that while I'm at it. But this will be on 5 different tests. Ne? Yeah.
Okay.
Okay, meaning yes, do it, or
Yeah.
okay,
Yeah.
do it.
Do it.
Okay, let's go back here. Let's get this. So some time ago, after identity tests, cosine 2x was 1 minus 2 sine squared x, right? And then if you solve for this, then you get this, right? Actually, I'm going to put it right next to each other. And there's another one that is also almost as good. Cosine 2x is equal to 2 cosine squared x minus 1. So if you want to know what cosine squared of x is, that's got to be 1 plus cosine 2x over 2. Okay? You're going to need to know these two on 5 different tests at least, I guarantee. Because this happens so many times. Any other question?